In this episode, we take a practical look at how network architecture and service design choices shape real security outcomes, especially when attackers, outages, and mistakes are part of everyday reality. Beginners often learn security as a list of controls, but architecture decisions are where those controls become effective or ineffective because architecture determines where trust exists, where it ends, and how damage is contained when something goes wrong. Network design influences who can talk to whom, how exposure is reduced, and how you limit blast radius when a system is compromised. Service-oriented architecture, SOA, influences how applications are decomposed into services, how services communicate, and how identity and authorization decisions are enforced across many moving parts. Threat realities are the practical patterns of risk you should assume, such as phishing leading to stolen credentials, misconfigurations exposing services, lateral movement after an initial compromise, and data exfiltration through legitimate-looking paths. The goal is to choose approaches that fit those realities rather than relying on outdated assumptions about where the danger lives. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A strong starting point is understanding what threat realities really means in architecture terms, because it is not just a dramatic phrase about hackers. Threat realities include the probability that credentials will be stolen, that some component will be misconfigured, that software will have vulnerabilities, and that privileged access will sometimes be misused or compromised. They also include the fact that networks fail in messy ways, such as partial outages, routing mistakes, or unexpected latency that tempts teams to bypass controls. Architecture must therefore assume that the perimeter will be probed, that insiders exist both as trusted staff and as compromised accounts, and that attackers will try to blend into normal traffic patterns. For network design, that means you cannot rely on one boundary and hope everything inside is safe, because many incidents begin inside through credential theft or vendor access. For SOA designs, it means you cannot assume service-to-service calls are automatically trustworthy just because they happen within the same environment. When you choose an architecture that matches these realities, you create friction for attackers where it matters, and you protect the organization from predictable failure patterns. Network architecture choices often begin with the idea of trust zones, which are areas where you assume a similar level of control and therefore allow a certain level of communication. In older models, the trust zone boundary was mainly the external perimeter, and the internal network was treated as a largely trusted space. Modern threat realities challenge that assumption because attackers often gain an internal foothold and then move laterally, so internal boundaries become as important as external ones. A good network architecture, therefore, defines multiple zones, such as user access areas, application tiers, management networks, and data stores, each with rules about allowed communication. The point is not to create complexity for its own sake, but to ensure that compromise of one zone does not automatically grant access to everything else. Beginners sometimes assume that segmentation is only for large enterprises, but even small environments benefit from basic separation of high-risk functions like administration and sensitive data. When trust zones are defined thoughtfully, network controls become a structural safety feature rather than a patchwork of rules. Perimeter design still matters, but the best perimeter designs recognize that the boundary is not a magical shield. It is one layer in a broader containment strategy. Perimeters reduce exposure by limiting what services are reachable from untrusted networks and by shaping how traffic enters and exits. A classic approach includes a demilitarized zone, DMZ, which is a boundary area where externally reachable services are placed so that compromise does not immediately expose internal systems. The DMZ concept remains useful because it formalizes the idea that public-facing components should be isolated and monitored more aggressively. Threat realities also include scanning, exploitation attempts, and abuse of exposed interfaces, so perimeter architecture must include thoughtful exposure management, such as limiting inbound paths, controlling outbound paths, and ensuring that public services do not have unnecessary direct access to sensitive internal resources. Beginners sometimes treat the perimeter as the only security concern, but in modern designs, the perimeter is a risk reduction tool that must be paired with strong internal controls. The best architecture uses the perimeter to reduce attack surface while still assuming that something might slip through. Segmentation is one of the most practical ways to match threat realities because it directly limits lateral movement, which is a common pattern after an initial compromise. Segmentation can be designed at multiple layers, including network boundaries, application boundaries, and identity boundaries, and the most effective designs use more than one layer. From a network perspective, segmentation means separating systems by function and sensitivity, and then allowing only the specific communication needed for business operations. This is where virtual local area network, VLAN, concepts often appear, not as a configuration detail, but as a way of thinking about how traffic is separated and controlled. The goal is to avoid flat networks where any compromised system can reach everything else, especially administrative interfaces and sensitive data stores. Segmentation also supports monitoring because it creates clear choke points where traffic is expected, making unusual movement more visible. Beginners sometimes worry that segmentation makes systems hard to operate, but good architecture uses segmentation with clear patterns so teams understand where to place components and what communications are allowed. When designed well, segmentation speeds response because containment actions can be targeted rather than disruptive. Another network architecture choice that must match threat realities is how you handle access from users and devices, because many compromises start with a user's credentials or endpoint. If your network assumes that any device inside a building or on a corporate network is safe, you are relying on a weak assumption in a world where malware and credential theft are common. A stronger approach is to design access based on verified identity and device posture, and to limit what a user can reach even after they authenticate. This idea often appears in the concept of zero trust, which is not a product or a single control, but a design stance that assumes trust must be continually earned rather than granted permanently. In architectural terms, it means you define clear access pathways, enforce strong authentication, and require authorization checks at the point of use rather than only at the network edge. It also means you treat administrative access as a special case with tighter controls, stronger monitoring, and narrower scope. Beginners sometimes interpret zero trust as distrust, but the real point is reducing the damage of inevitable compromise by limiting broad implicit trust. When user access architecture matches threat realities, stolen credentials become less powerful and easier to detect. Now we shift toward SOA, because service-based designs change where security decisions must live and how network boundaries are used. In a monolithic application, many controls can be centralized inside one codebase and one deployment boundary. But in SOA, functionality is distributed across many services that communicate constantly. This distribution increases agility, but it also increases the number of interactions that must be secured, logged, and understood. Threat realities in service environments include attackers abusing a weaker service to reach stronger services, exploiting overly broad service permissions, or finding gaps in how identity is propagated across calls. The architecture must therefore ensure that each service enforces authorization for the actions it performs, rather than trusting that a previous service already checked. This is a common beginner misunderstanding, where people assume the front door service protects everything behind it. But in distributed systems, internal calls can become an attack surface. The safest assumption is that each service must defend its own responsibilities using consistent identity and policy patterns. When SOA security is designed for reality, services become compartments rather than stepping stones for attackers. A critical concept in SOA security is the difference between authentication and authorization across service boundaries, because these are often confused in early learning. Authentication is proving who or what is making a request, while authorization is deciding what that identity is allowed to do. And in a service environment, both must be handled repeatedly and consistently. Services often communicate using an application programming interface, API, which is the defined contract for how requests are made and how responses are returned. That contract is not just a technical interface, because it becomes a security boundary where you must validate inputs, enforce access rules, and produce audit events. Threat realities include attackers calling internal API endpoints directly, replaying tokens, or exploiting inconsistent authorization rules across services. Architecture must therefore define how identity is represented in service calls, how permissions are scoped, and how services verify that a request is legitimate and authorized. This also includes deciding which services can call which other services, because internal traffic should not be treated as automatically safe. When you treat API boundaries as real security boundaries, you reduce the chance that distributed design turns into distributed vulnerability. Network architecture and SOA architecture meet in the question of where enforcement happens, because you can enforce some controls at the network layer and some at the service layer, and the best designs coordinate both. Network layer controls can restrict which services can communicate, which reduces attack paths and helps contain compromised components. Service layer controls enforce business rules and fine-grained permissions, which networks cannot understand because networks do not know what an order approval or data export means. Threat realities include the fact that attackers may be inside the network and may use legitimate communication paths, so relying only on network restrictions is not enough. At the same time, relying only on service layer controls can be risky if services are misconfigured or if a compromised service can reach too many others. A balanced architecture uses network segmentation to limit reachability and uses service authorization to limit actions, creating layered containment. Beginners sometimes look for one perfect enforcement point, but distributed systems benefit from multiple aligned layers because failure in one layer does not automatically break the whole security posture. When you make enforcement placement an intentional architectural choice, you reduce both complexity and surprise. Service discovery and dynamic scaling introduce another threat reality. Systems change constantly, so static assumptions about addresses and paths often break. In modern environments, services can move, replicate, or be replaced, which means security cannot depend on fixed locations alone. Architecture must therefore focus on identity-based trust and policy-based communication rather than relying purely on static network placement. That does not mean network design is irrelevant, but it does mean network rules should be expressed in terms of roles and allowed interactions rather than hard-coded assumptions that drift. Threat realities include misconfigurations that accidentally expose internal services or deployments that create unintended communication paths. A resilient design makes expected service interactions explicit and makes unexpected interactions stand out through monitoring and policy enforcement. It also ensures that privileged operational paths, such as management interfaces, are separated from normal service traffic so they cannot be reached casually. Beginners often underestimate how quickly dynamic environments evolve, and that is why matching architecture to threat realities requires designing for change as a normal condition. When the design assumes movement and scaling, security becomes more stable rather than more fragile. Observability is an architectural requirement in both network and SOA designs because detection and investigation depend on being able to reconstruct what happened across boundaries. In a service environment, a single user action can trigger many internal calls, and without consistent logging and correlation, you cannot tell whether behavior was normal or malicious. Network architecture can help by creating predictable choke points and by ensuring that critical traffic paths are observable, while service architecture must ensure that meaningful events are recorded at the point where decisions are made. Threat realities include attackers using valid credentials and valid interfaces, so the difference between normal and abnormal often appears in patterns, such as unusual call sequences, unusual data volumes, or unusual access times. Architecture must therefore support consistent identifiers so events can be linked across services and network paths, and it must protect evidence so attackers cannot easily erase their traces. Beginners sometimes think monitoring is something added later, but in distributed designs, monitoring must be built in because retrofitting correlation is painful and often incomplete. When observability is designed from the start, audits and incident response become calmer because the system can tell a coherent story. Another architectural decision that must match threat realities is how you handle secrets and trust material, because service environments often rely on credentials, keys, and tokens to authenticate internal communication. If secrets are spread widely or reused carelessly, compromise of one service can become compromise of many services. Architecture should therefore minimize where secrets live, scope them to the smallest necessary privileges, and ensure that secret use is traceable. It should also account for rotation and revocation, because threat realities include the possibility that secrets will be exposed and must be replaced quickly. Network segmentation can reduce the ability of an attacker to harvest secrets from multiple systems, but segmentation alone is not enough if secrets grant broad access across boundaries. A mature architecture treats secrets as high-value assets and designs service permissions so that even valid credentials cannot perform unlimited actions. Beginners sometimes assume that once a service is inside the environment, it should be trusted, but a compromised service is one of the most common and dangerous internal threats. When secrets and trust are designed with containment in mind, distributed systems become less brittle and more defensible. Choosing approaches that match threat realities also means accounting for performance and delivery pressure, because security designs fail when they demand perfect behavior from imperfect teams under constant deadlines. A network design that requires a unique rule for every interaction can become unmanageable, leading to broad exceptions that undo the intended protection. A service design that requires every team to invent its own authorization model can lead to inconsistent decisions and gaps. Architecture should therefore provide reusable patterns, clear defaults, and consistent expectations, such as how services authenticate, how they authorize actions, and how they log decisions. This reduces cognitive load and reduces the chance that security becomes an obstacle that teams bypass. Threat realities include human realities, such as misconfigurations, rushed deployments, and incomplete documentation. So good architecture makes the safe path the easiest path. It also defines how exceptions are handled so urgent needs do not destroy long-term safety. Beginners often think strong security must be complicated, but the strongest architectures are often the ones that are simple enough to be followed consistently. When simplicity supports consistency, threat resistance improves in practice. When you evaluate network and SOA approaches, you should train yourself to ask a few grounded questions that align architecture with real threats rather than abstract ideals. Where are the trust boundaries, and are they aligned with where data and control actually move? If one component is compromised, what can it reach next, and how quickly can you contain it without shutting down everything? Are authorization decisions enforced where actions occur, or are they assumed based on earlier checks that could be bypassed? Can you reconstruct a timeline of actions across services and network paths without relying on guesswork? Do the patterns scale as systems grow and change, or do they become so complex that teams will disable them under pressure? These questions keep you focused on threat realities like lateral movement, misuse of valid credentials, and hidden internal abuse of interfaces. They also help you choose the right balance between perimeter controls, segmentation, and service layer policy enforcement. If an approach cannot answer these questions well, it is likely to fail under real-world conditions even if it looks neat on paper. Architecture succeeds when it remains stable under stress and change. To close, choosing network and SOA architecture approaches that match threat realities is about designing trust, boundaries, and accountability for the world as it is, not the world as we wish it were. Network architecture contributes through thoughtful trust zones, perimeters that reduce exposure, segmentation that limits lateral movement, and access pathways that assume credentials can be stolen and devices can be compromised. SOA contributes through clear service boundaries, consistent API security expectations, repeated authorization at the point of action, and layered enforcement that combines network restrictions with service-level policy. Both approaches depend on observability and evidence, because detection and auditability require coherent event trails that survive incidents and change. Both approaches also require designs that teams can operate consistently, because complexity and ambiguity are vulnerabilities in their own right. When you align architecture decisions with realistic threat patterns, you build systems that are harder to exploit, easier to contain, and easier to defend under scrutiny, which is the outcome an ISSAP-level architect is expected to deliver.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.